Okay, so now let's get on to the tangent function. And tangent is very similar to the sine and cosine in terms of some of the characteristics that we're going to be looking for. However, the graph is completely different, as well as everything is not carried over from sine and cosine. So if you remember in our notes that we went through here, let's go and take a look here at the sine characteristics of cosine. We can see our initial period is from negative pi halves to pi halves, right? You can see the graph obviously repeats itself just like sine and cosine. But the period, though, is now going to be pi halves plus sine. Yep. Yeah. You can see that the period now is pi divided by b, and there's not an amplitude. And there's not an amplitude because the definition of an amplitude was half the distance from the max to the min. Well, the tangent function doesn't have a max or a min. The domain is a little confusing with the vertical asymptote, so we'll talk a little bit more about that. But besides period, phase shift, vertical shift, domain and range, like it's kind of the same. We just need to have these asymptotes now we need to take care of, as well as the asymptotes, as well as the period is going to be a change. So those are going to be kind of like our big differences that we're going to look at. So in this case, we're looking to identify the period, the phase shift, the vertical shift, asymptotes, domain, and reflection. So let's start with like the easy one, which would be identifying the period. And again, remember the period is just going to be 2 pi divided by b. So the period is just going to be 2 pi. I'm sorry, not pi, 2 pi. Geez, I'm already like starting the wrong one. That's just going to be pi divided by b, which in this case is pi. Cool. So period here is pi, which is just equal to 1. I don't have a phase shift. I'm not adding or subtracting inside the function. I do have a vertical transformation, which is shifting the graph up 1 unit. So I'll just say up 3. And then I need to identify where the new asymptotes are, as well as the domain and the reflections. So there are no reflections. So let's go and take a look at finding the asymptotes. So again, I think this is very important to kind of understand, again, our initial period. So our initial period here is between negative pi halves and pi halves. And I like to just kind of visualize this, and rather than kind of like scrolling up here, I think this is important to see. Okay, so there's the tangent graph. There's our initial period, and this graph just repeats itself. So we can see we have an asymptote here at negative pi halves and pi halves. And one thing that I talked about in the notes on this was that we could talk about the initial start and the initial end, or sorry, the initial period start and end. And what we notice about that for tangent is at the start and end of our initial period is an asymptote. So what's important about that is if I can figure out what is the kind of like transformations or change to my initial period, I can identify where the new asymptote is going to occur. And then again, from each asymptote, while we say that, yes, this distance is really, pi, it's really going to be the period, which can change. So that's going to be based on what our new period is, which in this case you can see is 1. So the first thing I'm going to do is take everything that's inside my function. So I'm going to have, so let's look at the asymptotes. Okay, so to find the vertical asymptotes, basically what I'm going to do is I'm going to take whatever's inside of my function, pi x, and set it equal to either my initial start or end. Now, I prefer to have the positive rather than the negative, so I'm going to choose pi halves. Okay, and then I'll just solve for x, which is just going to give me x equals 1/2. So that is going to be where my new asymptote is going to occur. And then all I need to do is just go ahead and add the period. Well, the period in this case is 1, so it'd be plus 1, and then we can add that constant n as many times, positive or negative. So my asymptote is going to be 1/2 plus 1n, or another way just to write that would be 1/2 plus n. And then the domain, we could write this a couple different ways. We can basically say, all real numbers such that x cannot equal 1/2 plus n. Okay, and obviously the range is going to be all real numbers, so that's why we're only focused on the n. And then if you want to go ahead and take a look at this, and again, I'm only graphing, I should graph the initial period here, right? So let's go and graph the initial period. So my period is 1. Now I do know my initial, let's see here, my initial start here is at my initial period is at 1/2. And since there's no phase shift, then that's going to go to, so if my end is at 1/2, then my initial start is going to be at -1/2. So I have -1/2 and +1/2. So I have some nice little dots, and there's been no shift up or down, left or right. Now, if you want to go ahead and check my answer, I created a link for all of the videos here, again, on Desmos. One important thing to note is Desmos is not going to tell you, where the asymptotes occur. So you're going to need to make sure that you understand where those asymptotes occur. So one thing you can do is just kind of do like a vertical line, x equals 1 divided by 2, and x equals, -1 divided by 2. And then, therefore, when I graph this, oh, I forgot to shift up 3. Crap. But either way, I'll come back to that. Sorry about that. Let me change this. Come on. Let's use black. There you go. As you can see, though, when I'm looking at this graph here, come on. You can see that the graph is approaching these asymptotes. And obviously these asymptotes are going to repeat a distance. And again, they are a period of 1 away from each other. So they're just going to keep on repeating from there. So fix this. Okay, now there is my shift right there. But again, I forgot to move along with this, that this graph is actually being shifted up 3, right? We don't want to forget that. And of course, I forgot that. So sorry about that. So let's go ahead and kind of sneak that in 3 units up, 1, 2, 3. So therefore the graph looks something like that. And then again, as you can see from Desmos, that graph just repeats itself, infinitely to the right and to the left. All right, let's move on to the next one. This negative is telling us, again, we're going to be reflecting about the x-axis. So I want to say, I'll just add that in there, start with that. Reflect the x-axis. You can see that I don't have a coefficient for my x, so I can say my period is just going to be pi. I do have a phase shift here. Since there's no b, I can just say it's going to be pi halves to the left. And then my vertical transformation is going to be up 1. All right. Now this one's kind of nice because I don't really have to do too much math with this, because if here's my initial period, if I'm basically have the exact same graph, same period, same x-axis, the only thing that's happening is the graph is just being shifted 1/2 to the left. Well, then I can figure this out. That's going to be then at -pi, and this would be at 0. So that's where my 2 asymptotes now are going to occur. And then the graph is going to look the same, except it's being reflected about the x-axis, right? So if you take this graph and reflect about the x-axis, you're going to have a graph that's going to look something like this. And then, don't forget, we also have to shift this graph up 1 unit. So I'm actually going to have a final graph that's going to look like that. Okay, so just make sure that you have that finalized graph. Now, as far as identifying the asymptotes, I kind of visualize this without having to do like any math here. Like this one, like math is going to be helpful. In this case, though, I can just say that, we see that the asymptote here is at, x, and then their each period after that. So, or at 0, and then each after that. So I can just say x, is equal to 0 plus pi n, because the next asymptote is going to occur at pi, or times pi times 1. The next one after that would be pi times 2. And we don't really need to write the 0 there, so x is just equal to pi n. If I wanted to write the domain, all real numbers, such that x cannot equal pi n. I don't know what I was writing there, but we'll run with that. All right. Next one. Now, this one confuses a lot of students here because they see the 3 and they immediately want to think amplitude. And again, we don't have an amplitude. Now, what I like to do is, just kind of look at that when you think about this graph that, what we looked at in class is, that's vertically stretching the graph. So the graph is just going to look a little bit skinnier than your typical initial period. But it's not the amplitude, because the amplitude, you have to have the max and the min, which we don't have for tangent. We do have a negative. And so we are going to want to rewrite that, so we can understand our b. So anyways, the 3, that's just going to, we can just, I'll just say a vertical stretch. Vertical stretch factor of 3. All right, and then after we have that vertical stretch factor of 3, then what we're going to be looking here is of identifying the period. And to identify the period, though, we want to know what our b is. So just remember that, negative x over 3, that can be rewritten as a negative 1/3 x. So that's going to be our b. And again, for period, for tangent, is going to be pi divided by b. We don't need to include the negative because, again, period is just going to be a positive length. And when we multiply by the reciprocal, we get 3 pi. We're not vertically shifting the graph left or right at all, but we are reflecting it about the y-axis. So we can say reflect the y-axis. Okay. To find the asymptotes, though, I think this might be helpful to go ahead and set our function equal to one of our asymptotes, which will do pi halves. And when I do that, I multiply by 3 and divide by negative. I'd get x equals a negative 3 pi halves. So this graph, rather than the initial period has an asymptote at pi halves, this graph now has an asymptote at negative 3 pi halves. And then again, remember, that's going to be plus the period, plus 3 pi n. So basically, all you need to do is take what's inside your function, set it equal to pi halves or set it equal to negative pi halves. Either way, there's multiple answers you could do here. Figure out, solve for x, and then just add the period n. And that is just basically the simple way to identify the asymptote. So therefore, our domain then is going to be all real numbers except for where all these asymptotes occur, such that x cannot equal negative 3 pi over 2 plus 3 pi n. So let's go ahead and sketch this. The graph isn't being shifted to the left or to the right at all. I am going to want to make sure I can represent this reflection, right? Because the tangent, instead of going down to the left and up to the right, it's going to be reflected. And then my new asymptotes now are at negative 3 pi over 2. And if that's my, what did I set that equal to? Oh, that probably wouldn't have been, well, I guess it really wouldn't have mattered. 3 pi halves, I probably don't really need to include the negative here, but you could use that either way. So we could say that's going to be negative 3 pi over 2 and a positive 3 pi over 2. And if you can see the distance from negative 3 over 2 to positive 3 pi over 2, you can see that distance equals to 3 pi. I actually would not include that positive there. Just because we know that's a reflection, that's actually not that's a reflection. Well, it's a reflection about the y-axis, but it's not going to be affecting where the asymptotes occur. So it's really just going to be kind of more confusing in that state. But you can still use it. It's not wrong, but you'd still get the next asymptote from there, but I'd prefer just stay away from negatives. So, and then there's no more vertical shifts or down. So now my graph is basically just going to look like this. So now it's going to be looking in the opposite direction. Boom. All right, next one. Tangent, y equals tangent of negative x divided by 2 minus pi. All right, looks good, but I have a negative I don't like, and I have a 2. So I'm going to want to get those out. And some people might not be comfortable with dividing this out. So I'll work through it the initial period way as well. Just to kind of confirm my results. So first of all, let's rewrite this. So negative x over 2 minus pi. All right, let's rewrite this as a negative 1/2 x minus pi. That helps me divide out the negative 1/2, and then I'd get x plus 2 pi. Now, if you're not following me, just apply distributive property back. Negative 1/2 times x is negative x, negative 1/2 x, which is negative x over 2, and negative 1/2 times 2 pi is negative pi. What we can also do is also just take whatever's inside the function and then set it to one of our initial periods, either the start or the end. Doesn't really matter which one, but I will use the end because I like positives. When I add pi to both sides, I'm going to change pi to 2 pi over 2. So this would be a negative x over 2 plus, equals pi halves. And instead of pi, I'm going to write it as 2 pi over 2 because 2 pi over 2 is the same thing as pi. Therefore, I can add these up. So I get negative x over 2 is equal to 3 pi halves. And then you could just like divide out the 2's, or mathematically, we'd want to multiply by a negative 2 on both sides. And those would divide out, and we'd just be left with a x is equal to negative 3 pi. And that's not right. Negative, what'd I do? That's pi. Oh, that's 2 pi over 2. I got to figure out my mistake. Crap. Negative pi halves. Negative pi over 2. Factor that out. That leaves you with an x plus pi halves. Okay. And then this one, I add that. That's 2 pi over 2. Crap. I hate when this happens. All right. Negative pi halves. Factor out the negative. That becomes negative pi halves x. That becomes a negative x. That's right. Something's wrong here. Equals pi halves. That's correct. Oh. Well, why don't we set it equal to a negative pi halves? Let's do the other x-intercept, because x equals 3 units to the left. That's saying 2 units to the right. 3 units to the left would be same units as 2 units to the left. So let's do it as a negative 3 halves. So that'd be a negative pi over 2. And so, okay, so we're going to change this to, instead of using the positive asymptote, because 3 units to the right or 3 units to the left is going to be same as 2 units to the right. So let's go ahead and verify this as, rather than using okay, I'm going to keep that. But let's just do it the other way. Let's take negative x over 2 minus pi is equal to negative pi halves. And we'll look at this one on Desmos. When I go and add this one, I get negative x over 2 is equal to negative pi halves plus 2 pi over 2. What is going on? Negative pi halves. That's a negative and that's a negative. That should be a positive. Oh, that's where I went wrong. Okay, so I'm going to start this whole thing over. Whole thing over. So we're going to have to refresh. Okay, so now that we've factored that out, now we can work on this in another direction. And that would be simply just setting our setting the negative x over 2 minus pi, setting that equal to one of our intercepts. So I'd have negative x over 2 minus pi is going to be equal to a negative, one of our intercepts to be pi halves. And that's a horrible x here. So when I go ahead and add pi to both sides, and I can rewrite that as 2 pi over 2. I'd have a negative x over 2 plus, or equals,